right? So based on our last lecture, based on Ampere's law, I had given you this question in the worksheet. Consider a current I flowing along a wire whose shape is represented by the equation. So this equation represents the shape of the wire.
క్లాస్ ఒక నిమిషం అది అది కట్
Keep yourself muted, all of you. Okay. So yeah, this equation represents the shape of the wire. It's an equation between y and x. So the wire lies in the xy plane. Okay, assume z coordinate is 0. You have to calculate integral b dot dl over the path represented by this circle. Okay, so a wire is given and a circle is given. The wire again. Okay, just a moment. Right. So the wire carrying current produces a magnetic field. We have to integrate b dot dl over this path. Okay, so any answer, any of you? Try it now. I'll give you 2 minutes. Visualize current flowing along this path. Visualize the circular path that is given to you. Can any of you quickly tell me the roots of that equation y is equal to x square minus 8x plus 12? Or at least the shape of that wire represented by that equation. Okay, I got one answer for roots as 6 and 2. That is correct. And what is the shape of the wire represented by that equation? It's a quadratic equation, so the shape will be a parabola, right? So the wire is in a parabolic shape in the xy plane. And let us draw that parabola. The roots are 2 and 6, correct? So maybe x is equal to 2, maybe somewhere here. X is equal to 6, maybe somewhere here. So the shape of the wire, put x as 0, y is 12. So cuts the y-axis somewhere here. I'm not calculating where the minimum is and all. It's not necessary. Let this be the wire. Okay, so this is x is 2, this is x is equal to 6. So current flows along this orange path. So usually what they do is they show you the wire and ask you what is integral b dot dl. Instead of showing the wire, I have given you an equation which represents the path along which the current flows. So it's like the wire is like this. Now you can take current this way or this way. That's your choice. In the answer, I only expect the magnitude. So let's say there is a current I flowing this way. Okay. The next thing we need to do is visualize the path along which we have to take closed integral b dot dl or simply integral b dot dl. Since it's a circle, it's a closed path. Can any of you tell me what will the radius of the circle be? I'm sure you must have studied circles in 11th class. X square plus z square is equal to 16. How to draw that circle? It's a circle of radius 4 units. Okay, basic circle equation. Okay, there are complicated equations as well. This is the simplest equation I know for a circle, so I've used that. So basically, this is a circle. Where is its center? x square plus z square is equal to 16. Center is at origin. You can write 0, 0, 0, and radius is 4 units. Usually x square plus y square is equal to r square, something like that. This is in the xz plane. Okay, so x square plus z square. Let's visualize that circle. Radius is 4 units. 4 units will be here. So the circle cuts through these points. You can imagine it somewhat like this. We are looking at it from an angle, so it won't appear like a proper circle. Somewhat like that. Okay, if you look at it properly from the y-axis, it will appear like a circle, but we are looking at it from an angle, as I said. Right. So this circle is in the xz plane, right? The horizontal plane. Current is flowing this way. Let me just make the diagram clear. Right, now it's fine. Okay, y-axis. It'll be like this. So tell me, what will be integral b dot dl over this circular path? It's like half the circle is coming out in the positive z direction, half the circle is behind. Okay, negative z. It's a closed path. Okay, circle is a closed path only. And we need integral b dot dl along this circle. So basically what we need is closed integral b dot dl. According to Ampere's law, what is closed integral b dot dl equal to over any closed path? One of you just tell me the formula for Ampere's law. Rishi, any idea? Basic formula for Ampere's law. Last class, that is what we had discussed. Looks like you all didn't practice at all. So closed integral b dot dl will be equal to plus or minus mu naught into I. Yeah, you typed your answer. You could have unmuted. Okay, I removed that unmute option, I think. Fine. Okay. So we need closed integral b dot dl, and that is equal to mu naught into I enclosed. I'm only considering the magnitude, not the direction. Now tell me, that green loop, the circle that we have taken, is it enclosing any current? Is any current passing or cutting through that loop or not? And how much? Just a moment, I'll allow you all to unmute. Yeah, if any of you wants to answer, you can unmute and answer. How much current is that green loop enclosing?
So is it minus 4 amperes?
Where did you get a number from?
Sorry, sir.
Current is I. The current in the wire is just I. So how much current is passing through that loop is my question, is cutting through that loop. Is it not obvious from the diagram? Like, how much current is the loop enclosing?
I only, sir.
I only, no? The wire is going from inside the loop, and on the other side it is coming up from outside the loop. So there is a current I flowing in here into the loop, and it's going out somewhere here. Okay, so that doesn't count. This will count. This is the enclosed current. So the green loop that we have taken, the circular loop, is enclosing a current I. Okay, that's all. So the answer will be mu naught I. Suppose I had given you a circle whose radius is, let's say, 8 units. maybe somewhat like this. What will be closed integral b dot dl for that path? The circle is in the xz plane itself. Okay, but you can see how the current is flowing. It is going down, again it is coming up inside the circle itself. In that case,
So
what will be?
is it gonna be mu naught I itself?
Why? Do you say the enclosed current is still only I?
Yeah, it's only I, sir. It doesn't change, right?
But look, there is an I going down here, and there is also an I coming up here, right?
Yes, sir.
So there is it's like one current, if you call it a positive current, the other current will be taken as negative. Okay. So it's like the net current enclosed by that yellow loop is 0. Because there's some current going this way and equal amount of current coming up this way. So the net current becomes 0.
Okay, sir.
Then in that case, closed integral b dot dl becomes 0. So this question is to test like both little bit of physics and little bit of mathematics also. Okay, and in JEE, you can very well expect such questions. Okay, let's try one more question from the worksheet. So along a certain path of length L, okay, you're not given the shape of the path, but the total length of the path is L. It is found that integral b dot dl is equal to k, some value. Okay. Right. Can we conclude that B, that's the magnitude of the magnetic field at any point along that path? Okay, when can we conclude that it is equal to k by L? Any answer? We know the length of the path and we know this integral b dot dl value is k. Can we say that B is equal to k by L? If yes, in which case can we say? Think about it. I got one answer as dot product becomes 1 at 0 degrees. Okay, cos theta becomes 1. Dot product doesn't become 1. When angle is 0, cos theta becomes 1. Okay, then I got one more answer as the angle needs to be 0. The angle between B and DL needs to be 0 everywhere. Okay. Fine. Listen. We know the value of integral B dot DL is K. We want the condition when B will be equal to K by L. Now L here, as given in the question, is the total length of the path. So automatically L becomes integral DL without a vector symbol on it. You add all the small lengths of along that path, it becomes the total length. Okay. So we want B to be equal to K by L. That's the question. For that case, we have to derive a condition. Now, if you want B to be equal to K by L, that means BL should be equal to K. That means B integral DL should be equal to K, which means you should be able to get B out of the integral. Then this will be true, right? So now you have to think along those lines. When can we get B out of the integral? Only the magnitude of magnetic field should come out of the integral. And there should be no other terms. Tell me generally, when can you put something outside an integral?
When it is uniform throughout the integral.
That term which you want to put outside the integral has to be constant or uniform, right? That means now you want for the given condition to be satisfied, b should come out of the integral. That means the value of b should be same everywhere. And what is b here? The magnitude of magnetic field. So b should be uniform. Magnitude should be uniform. Direction need not be, because this is not b vector, it's just b magnitude. Okay. So magnitude of the field has to be uniform. That's one thing. Okay. But see, in the actual integral, what we have is b vector. Only its magnitude should come out. Means we have to remove the dot product first. We have to evaluate the dot product first. Okay. Now in integral b dot dl, simply applying the formula for dot product, you can say it is equal to b dl cos theta. Now here b must come out, so b should be uniform. And to get the result that we want, there should be no cos theta term there. Okay, that means cos theta should become equal to 1 everywhere. It should be constant and it should be equal to 1 everywhere. Fine. So there are two things that are needed, or there are two conditions that are to be satisfied for b to be equal to k by L. One is the magnitude of magnetic field b must be same everywhere along that path. One more thing is theta should be 0 everywhere along that path. What is theta here? Theta is the angle between magnetic field b and the vector dl. Okay, so the answer becomes when magnitude of field is uniform over the path and the angle between b and dl is 0 all along the path. In such cases, you can directly tell b is equal to k by L. Okay. And why this is needed is, why I gave you this particular question in the worksheet is because we will be using Ampere's law. Okay. See, Ampere's law is written like this. Closed integral b dot dl is equal to mu naught into I enclosed. Right. We sometimes use Ampere's law to derive the magnetic field. Okay. Means from this, you have to get only b. Right. So to be able to get b from this integral, there are some conditions that need to be satisfied. You need to choose a closed path over which the magnitude of b is same everywhere. Then you will be able to take it out of the integral. And it will be better, even better, if cos theta is 1 everywhere. Fine. Then the answer will be k by L. Now I'm not saying b should only be k by L, but for b to be equal to k by L, that's the condition. Right. So if you want to find out magnetic field strength using Ampere's law, if you want to put it out of the integral, there are some conditions that need to be satisfied. Okay. Fine. Okay, just a moment. Yash has sent me one question. We'll discuss that. Okay, try this, all of you. A current I flows along a round loop. Round loop, you take it as a circle. Okay. If needed, take its radius as r also. You need to integrate b dr along the axis. I think this should be integral b dot dl or b dot dx, something like that. Like that r term is slightly misleading. Let's take it as x. Okay. So we'll treat it as integral b dx. It should actually be b dot dx. Anyway, the dot product will get removed easy only. And where do we want to integrate that, or along which path do we want to integrate that? Integral b dot dx along the axis of the loop from minus infinity to plus infinity. Okay, let us understand the question first. A current I flows along a round loop. Let us visualize that. And they're talking about integrating on the axis. So we need to visualize a round loop and its axis. We'll do that first. Let's say this is the round loop. There are different ways to solve, many ways to solve a question. Half of this loop will be out of the screen. The other half will be behind the screen. The part behind the screen, I'm drawing in dotted line. Okay. Next, we need to visualize its axis. Axis passes through the center of the loop and it will be a straight line perpendicular to the loop. Somewhat like this. Okay. They want you to integrate b dot dx along that axis from minus infinity to plus infinity. Now there is a current I flowing in this loop. Assume its radius is capital R. Fine. Can any of you think of a way to do this? See, they only want integral b dot dx. So are they asking you to integrate over a closed loop or an open loop? I can't call it a loop. Are they asking you to integrate over a closed path or an open path? That's my question. I got one answer as closed. Listen, if they want you to integrate over a closed path, no, they'll put a ring around the integral like this. Okay. And also here the path is visible. They're asking you to perform that integral along the axis. Okay. The axis of a ring, okay, the axis of a circular loop is a straight line. So you can't call it as a closed path. There are some cases in which you can take it to be part of a closed path. We'll discuss that. But as such, it's not a closed path. No, it's a straight line. Straight line is not a closed path. So they want you to integrate b dot dx or b dot dl over an open path. So it's clear that we can't directly apply Ampere's law and say it is mu naught into I. Okay, because the path is not a closed path. If you cannot apply Ampere's law, what other way do you have to integrate b dot dl? Anyone? Or if there is no closed integral, if you can't use Ampere's law, what is the only other way possible? You have to write the expression for magnetic field and integrate. Okay, you have to actually take the expression for B, multiply it with dx, or take dot product with dx and integrate with proper limits. What else can we do? Tell me, do we know the magnetic field along the axis of a circular loop? At any random point along the axis of a circular loop? Are you people revising or not? We derived the
Yeah.
magnetic field on the axis of a circular loop. Yeah, yes, tell me, you unmuted, but I didn't get any answer from you.
Sir, it is mu naught I r square by 2 into r square plus x square whole power 3 by 2.
R square plus x square whole power 3 by 2, where x is this distance to the point from the center of the loop. This is x. Okay, so that's the expression for magnetic field. We have to multiply that with dx, that's all. Now the direction of this magnet, we have to take a dot product between b and dx. We'll do that. Based on the current flow here, okay, can any of you tell me the direction of magnetic field produced by this loop?
Towards the left. Sir.
Towards left, you just have to curl your right hand fingers along the flow of current. The solid part of the wire is out of the screen. So in the part of the wire which is out of your screen, the current is going up. Behind the screen, the current is coming down. So to you, I guess this is left. So current will be flowing this way. Not current, sorry. Magnetic field will be created this way. So magnetic field is in this direction. Everywhere along the axis, it will be in that direction itself. Okay. Next, we have to take dot product with dx. Now dx is along the axis only. So dx would be like this. Like this or in the opposite direction, doesn't matter. The answers are all positive. So we'll only give the magnitude as the answer. What is the angle between b and dx? Obviously it is 0. So b dot dx simply becomes b dx in this case. And that is what we need to integrate. Okay, it is b dx cos theta. Theta is 0, so cos 0 becomes 1. That's why I didn't write that term. Okay, so we need to integrate mu naught I r square by 2 into r square plus x square whole power 3 by 2 dx from x is equal to minus infinity to x is equal to plus infinity. Let's put the constants outside. What are all the constants? Mu naught I r square 2. These are all constants. Put them aside. I'll call it k. You will be left with integral dx by r square plus x square whole power 3 by 2. Okay. Any idea how to integrate this? Generally, what do you do when you have a square plus x square or r square plus x square in the denominator of an integral?
Substitution, sir.
You will use
X
integration.
equals r tan theta.
X equal to r tan theta, correct. Here also you can visualize it if you want. X is that horizontal distance. Imagine joining the edge of the ring, edge of the loop to that point and calling this angle as theta. Then tan theta becomes, for theta, the opposite side is r, the adjacent side is x. Tan theta is equal to r by x. So it's like r is equal to x tan theta in this case, if that is what you want to call as theta. If you want to call some other angle as theta, for example, you may take this angle as theta, right? If you take this as theta, then x is the opposite side, r is the adjacent side, then tan theta becomes x by r, x becomes r tan theta. Nothing wrong in that. You can do it that way also. I think the difference will be in a minus sign, that's all. Okay. Let's take this angle itself to avoid confusion. Fine. So tan theta is equal to opposite x divided by adjacent r. So x becomes r tan theta. I'm going to use that substitution. But when you substitute this, you have to, you are changing the variable. You are changing x to theta. Then you have to change the limits accordingly. Now see, when x tends to plus infinity, that means if the point is on that side very far away, how much will this angle become?
90 degrees.
90 degrees, pi by 2. Then on this side also it will become pi by 2. So I have to take it as minus pi by 2. Limits will be from minus pi by 2 to plus pi by 2. Okay. Or plus to minus. Finally, we are going to make the answer positive. So hope the limits are clear. When x tends to infinity, this yellow line that I have drawn tends to become parallel to the gray axis that is there. Okay. So theta tends to become 90 on this side. On the other side, we'll take it as minus 90. So limits for theta will be from minus 90 to plus 90. And when you are changing the variable, you have to change dx to d theta also. Now we know x is equal to r tan theta. Differentiate both sides. You get dx is equal to r. Tan theta derivative is secant square theta d theta. So dx changes to this. Therefore, the required integral now becomes, we needed integral b dot dx. That now becomes, the constant k stays as it is. Integral, in place of dx, we'll write r secant square theta d theta divided by r square plus x square. Now we took x as r tan theta, right? So when you square x, it becomes r square tan square theta. In the denominator, you can take r square common and you will be left with 1 plus tan square. What is 1 plus tan square theta?
X square theta.
Secant square theta. So the denominator effectively becomes r square secant square theta whole power 3 by 2. That is nothing but r cube secant cube theta. Okay. Now cancel anything if possible. Secant square, 1 secant will be left. Send it to the numerator. Therefore, the required integral effectively becomes k by r square. Denominator secant, if you send to numerator, it becomes cos theta d theta. Limits from minus pi by 2 to plus pi by 2. Integral cos theta is sin theta. So we'll make adjustments there. from minus pi by 2 to pi by 2. Sine pi by 2 is 1. Minus of sine pi minus pi by 2 is minus 1. 1 minus of minus 1 becomes 2. So the integral effectively becomes 2. And k by r square. What was k? Mu naught I r square by 2. So this becomes mu naught I r square by 2 by r square into 2. Integral became 2. So answer is mu naught I. Okay. So see, it was an open path and you were asked to do integral b dot dl. Then write the expression for b and integrate. That's all. This is one way to answer. There is another way also to approach such problems. The given path is a straight path. Okay. It's not closed, but it's extending from minus infinity to plus infinity, right? You can assume it gets closed at infinity like this. Now tell me, what is the current this path is enclosing? Now we have formed a closed path. Or see, think of it this way. Think of it this way. It's a current loop, current carrying loop, right? Round loop. It's of finite size. The loop is of finite size. Now tell me, a finite sized loop having a finite amount of current, how much magnetic field can it produce at infinity? Any answer?
So can you repeat the question once?
It's a finite sized current loop carrying a finite amount of current. How much magnetic field can it produce at infinity or very far away from itself?
Sir, will it be like a point charge?
In magnetism, you can't call it a point charge, but what will the field be tending to when you go off to infinity?
Zero, sir.
0. Okay. Now they wanted you to integrate b dot dl over this path, over this straight path. Now that straight path itself is infinitely long. Okay. So here at the end of that straight path, I mean infinity, there's no end actually, but here the magnetic field is approximately 0 at that end, or as you go towards that end. Magnetic field is approximately 0. At this end also magnetic field is approximately 0. Then integral b dot dl also will start becoming 0, no? Up to some distance on that side of the loop and this side of the loop, b dot dl will be a finite value. But when you go too far on either side of the loop, okay, too far away from the center of the loop, magnetic field will tend to become 0. Then integral b dot dl also will tend to become 0 as you go very far away. And after that, what you do, you close this path. Okay. Everywhere, all over this large path that is there, the magnetic field due to this loop will be 0 itself because those points are very far away from it. Okay. So if you do integral b dot dl over this closed path, effectively you will be getting integral b dot dl over this straight path itself. Because for the remaining part b is 0, integral b dot dl is also 0 anyway. Okay. What I'm saying is call this part as A and call the remaining part as B. So total closed integral b dot dl is basically integral b dot dl over the part A plus integral b dot dl over the part B. Okay, that infinitely large closed path, I'm splitting it into two parts. One is the straight path along which you are asked to find out the integral. The other is the curved path. Okay, so total integral over that curved path will be the integral over the total integral over the closed path will be integral over the straight path plus integral over the curved path. That's what I have done. You are asked to calculate this value. Okay. This is going to be 0. Why? Because that path B that is there is very far away from the loop. Magnetic field anywhere on that curved path is 0. So integral b dot dl on that curved path will also be 0. Therefore, the answer that you are looking for is effectively closed integral b dot dl over an infinitely large path. Okay. And that infinitely large path, which I have drawn in gray, effectively encloses the current I. Okay, because you know how the current is flowing in that loop. No, it is going in from the upper point and it is coming out from the lower point. So it's just going into the loop once. Coming out is from outside the loop, so that doesn't count. Current enclosed is here, I. So integral for that whole loop will be mu naught I. That itself will be the answer that we are looking for. You could have answered it this way also without using the expression for magnetic field and all. Okay, any doubt in this? Fine, let's solve one more problem. That other problem is actually from, I mean, it's there in your syllabus also. Just a moment. Magnetic field at a random point inside a long cylindrical conducting wire carrying a current I. Okay, so there is a thick wire, the wire's radius is R, and there's a current I flowing through that wire. Okay, you can see the currents flowing. Total current is I. Okay, so this is when viewed from an angle, and this is the top view. You need to calculate the magnetic field produced by this current inside the wire at a point P. Okay, I had given you the steps also, but if any of you have done it, can you tell the answer? If you didn't do it, we'll discuss now. We have to calculate the magnetic field at the point P. How to do that? Okay, listen. See, it's one wire. The total current in the wire is I, but you are asked to find magnetic field inside the wire itself, not outside. So you have to think of the current I as a collection of small currents. Okay, as I have shown in the diagrams here, you have to think of current I as a collection of many DIs like this. Okay, each small current you take it as DI. So there are many streams of current passing through the cross section of that wire. All of them together become equal to I. Okay. Now our aim is to calculate the magnetic field at the point P. Every stream of current here, okay, like I highlighted one DI, I wrote one DI there, right? That DI will be flowing along this path. And it's an infinitely long cylindrical wire. So this stream of current DI will also be an infinite straight current. So effectively what happens here, there are many straight currents like this flowing along the cylinder parallel to its axis. So it's a collection of infinite straight current carrying wires, and we have to find out their magnetic field at one point. Okay. If there are infinite elements producing magnetic fields and you have to find out the net magnetic field, what do we generally do? If there are many elements producing a magnetic field and we need the net field, what do we do generally?
We integrate them. Sir.
You write expression for field produced by one element and you try to integrate it. That is one way to do. Another way to do is to use some laws which make things easy for us sometimes. Okay, let's see. Let us try to use the element method. If you want to use the element method, what you have to do is you have to consider one of the DIs. Okay, I'll highlight one of the DIs here randomly. Maybe this current. You have to write an expression for the magnetic field that it produces at this point P. Since the current is DI, it produces small magnetic field dB. You have to write an expression for it. And magnetic field is a vector quantity. So you should first write dB expression. Then you have to take dB's component. because magnetic field is a vector quantity. No, if you want to integrate vectors, you have to take their components, because all vectors may not be in the same direction. All vectors that you're trying to integrate may not be in the same direction. So you have to take its components, and then you have to integrate the component of dB. These are the steps you need to follow if you want to use the element method. Okay, let's try it. If it is easy to do, fine, we can proceed. Otherwise, we'll have to use some other idea. So for that purpose, I had given you another diagram also using the figure shown below. Just a moment. Yeah, using the figure shown below, try to predict the direction of net magnetic field at point P. Now, why do we care about net magnetic field at the point P? Because each stream of current Di will produce a magnetic field dB at the point P. But you will have to integrate all of them to get the net field. And fields are vector quantities. If you want to integrate vectors, you'll have to take components. So if you can visualize the direction of net field, for example, in this case, let's say net field is going to be this way. Suppose you somehow get to know that the net field is going to be this way, then the direction of dB, sorry, not the direction, the component of dB, like in this case, dB will be this way. The magnetic field produced by that current will be in this direction. If you know that the net field is going to be along the x-axis, then take dB's x component and integrate only the x component. Why bother about the other components which are going to get cancelled? Okay. So this is a general procedure we follow, right? All the way from electric fields, we have been doing that. Okay. If you want to find the electric field of a distribution of charges, we take an element of charge, okay, elemental charge. We write an expression for the field it produces somewhere. Then we take component of that field in the direction of net field and integrate only that component. Okay, so same thing you can do for magnetic field. So let us visualize the direction of net field first. If you consider this current, dot indicates the current is flowing out of your screen. Okay, current is flowing out of your screen and you can see where the point P is. Seshank, tell me, what is the direction of magnetic field produced by this green current at the point P? Rough direction you tell.
Downwards, I guess. If you use the thumb rule.
You're saying negative y. So you're saying
Yeah.
this direction.
Yeah.
How did you apply right hand thumb rule to get that direction? Which way should the thumb point?
The thumb points in the direction of the current towards
Thumb
me.
points in the direction of current. This green current is out of the screen.
So the
So the
thumb should
thumb
point
should be
towards
out of the screen. Yeah. And your finger should be pointed this way, right?
Yeah.
Towards the point where you want the magnetic field. Now, if your fingers are pointed this way and thumb is out of your screen, your palm will be facing this way. It won't be facing negative y direction. No?
What direction is that?
What direction?
Is the magnetic field? What do you call this?
You can say bottom right or something like that, or downward, slightly tilted to the right. I just asked for a rough direction. Okay. Yeah.
Okay.
So basically it has to be perpendicular to this vector. So it'll be like this. This is one magnetic field that you get due to that green current. Okay. Next, I'll take this blue one, assume it is on that x-axis. Yes, you tell me, what is the direction of magnetic field produced by this blue current at the point P?
Now it will be minus y-axis, sir.
In this case, it will be the
Along the
negative
minus
y-axis.
y-axis.
Correct. It will be like this. So you get one magnetic field this way. Of course, they are of different strengths. That point also needs to be considered, because how much magnetic field is produced depends on how close the stream of current Di is or how far it is. Okay, so field strengths will be different. Let's take some more currents. Say this yellow one. it will produce magnetic field like this. Next, on the lower side, if you take this one, pink, it will produce magnetic field like this. Let's take one more, maybe in purple. It will produce magnetic field this way. Okay, so you will get fields, different fields in different directions. Can you predict the direction of net field in this case? Anyone? Can you predict the direction of net magnetic field in this case?
Will it be positive x-axis? Positive x.
So you are saying it will be to the right. Okay, wait, we have not visualized some vectors. There are some vectors from this side also. No? Like there will be a current here. Take this one. This one over here, if you see, produce a magnetic field in this direction, it will be quite strong. And let's take one here. This one over here will produce a magnetic field this way. This will also be quite strong. So you'll get fields in all the directions actually. Then can you visualize the direction of net field?
But most of the vectors point in the positive x direction.
No, most of the vectors don't point in the positive x direction. Actually, wait, how did we get those vectors? No, let us do this once again. There are some mistakes in this. Let's start from the beginning, one by one. So let's take this current first, assume it's on the x-axis. So thumb points outwards, fingers point towards the point P. Then it will create a magnetic field this way. Let it be. Okay, done. Okay, let me mark that. Now take another current, say this one. Thumb points out of the screen, fingers towards the point P. Then it will create a magnetic field like this. Okay. Next, let us take this one, yellow. Thumb out of the screen, fingers this way, magnetic field will be like this. Next, let's take some on the lower side. Yeah, Mansa, your answer is correct only. Let's visualize that first. Take this current. Thumb points out of the screen, fingers point this way, then the magnetic field that it creates will be like this. It won't be pointed that way, it will be pointed downwards only. Next, one more we can take in green, let's say this one. Thumb out of the screen, fingers this way, then the magnetic field will be like this. Okay, so basically what happens is you will get a bunch of vectors directed like this. Of course, they'll be having different magnitudes and all. Can you think of the direction of their resultant now? Yeah, Manasa, yes, your answers are correct only. Rishi, what do you say? What do you think could be the direction of resultant of these vectors?
The negative y-axis.
Negative y-axis. Okay. Shashank, are you convinced with that or not?
Yes.
Right. Now, negative y at that point is actually tangential to this circle. If you imagine a circle here having a radius x, then that negative y direction is the tangential direction. So not just at that point, at every point on that circle or every point at that distance x, the magnetic fields are going to be like this. Okay, tangential to that circle. Okay. Now our aim is to derive the magnetic field at one of those points, at the point which is at a distance x. Now we were checking if we could use the element method to do this. The element method is almost impossible to apply here because you first need to write the expression for magnetic field produced by one element. Let's consider this di. you don't know the expression for the distance from here to here. The di is a straight wire that we have visualized. These are all straight wires. We know the formula for field produced by a straight wire, but for that you need to know the distance from the straight wire. That is not known. Okay, it's a random element. Fine. So if you write a random distance, it becomes very difficult to integrate. This angle is variable from element to element, because the magnetic fields are in different directions. For taking components, you will need those angles. So it becomes extremely difficult to write expressions for all those. So the element method is not going to be very useful to derive the net magnetic field in this case. If you can't use elements, the only other way you have to derive magnetic field, if you want to, is by using Ampere's law. Integral B dot dl, closed integral B dot dl is equal to mu naught into I enclosed. For that, you first need to visualize a closed path and see, you have to keep your aim in mind. The aim is to derive the magnetic field, right? If you want to get magnetic field using this formula, the dot product should be very easy to evaluate. Okay. And if you want to get magnetic field from this formula, you should be able to get B out of the integral. So you should choose a path over which B has the same magnitude everywhere. Okay. Either this dot product should become 0, or B should have the same magnitude everywhere, so that even when the dot product is non-zero, B can be kept out of the integral. You have to choose a path like that. And in this case, it's quite obvious. What is the path that you're going to choose? A path which will make integrating B dot dl easy. How should it be? It will be a circle in this case. Okay. So you will consider a circular path of radius x like this. So over that circle, the magnetic field at every point is in the tangential direction. Here it is like this, here it will be this way, here it will be this way. So this circular path makes integrating B dot dl very easy, because everywhere on that circle, B direction and dl direction, dl, imagine moving along that circle, you'll be moving parallel to the magnetic field at every point. Okay. So at each point, B direction and dl direction are the same. So angle becomes 0. Evaluating the dot product becomes easy. And why did we choose a circle? Another reason is that over this circle, every point is at the same distance from the center. They are all at a distance x. So the magnetic field will be same at all these points. Why will they be different? Every point is at the same distance. No, the way the points are placed relative to the currents is the same. So they should all those points should have the same magnetic field. Okay. So these are the factors that you need to consider. I'm sure many of you would have done this question already, but you have to think deep like this before you apply Ampere's law. You should ensure that integral B dot dl becomes easy to evaluate. Okay, now we have taken a path like this. So what is the path? We call it as an Amperean loop. IAN or EAN, I don't know, Amperean loop. Basically, it's a circle of radius equal to x. And that circle clearly encloses some amount of current. It doesn't enclose all the current, but it encloses some current. Okay. So over that circle, if you do integral B dot dl, closed integral, it simply becomes B dl cos 0. Because everywhere on that circle, B and dl are in the same direction. Becomes equal to mu naught into I enclosed. Okay, cos 0 is 1. And everywhere on that circle, B is same, put it outside the integral. If you put B outside the integral, you will be left with integral dl. Integrate the length of that path. It becomes the length of the circle 2 pi x. So left hand side becomes B into 2 pi x is equal to mu naught multiplied with current enclosed by that circular path. Now tell me an idea to find out how much current that circular path encloses. Let us visualize that path in this diagram. The circular path is somewhat like this. You can see that all the current streams are not enclosed by that circle. How to find out how much current is enclosed by that circle?
Sir, we can take help of current density.
That's all. Okay. See, that circle is part of a cross section of that wire, right? So, and we know the current is spread uniformly, it is distributed uniformly. So total current divided by total cross-sectional area should be equal to current enclosed divided by area enclosed by that circular loop. That's all. So the enclosed current simply becomes Ix square by R square. That's all. And then you can get the magnetic field. Therefore, B into 2 pi x becomes equal to mu naught I enclosed. Enclosed is Ix square by R square. 1x gets cancelled. You will see that magnetic field is proportional to x. This is what is interesting. Keep this in mind. If you want a magnetic field which is proportional to the distance from an axis, okay, you have to take currents like this. There could be some other arrangements also which can produce fields like, but this current, I mean, this kind of current flow produces a magnetic field proportional to the distance. Okay. And this is valid as long as x is less than or equal to r. Means inside the cylinder. Once you go outside, the result will vary. Okay. Can one of you quickly recollect and tell me what kind of charge distribution produces an electric field which is proportional to distance? In electrostatics, where did we get electric field proportional to x? You can even think in terms of gravitation. Where was the gravitational field proportional to distance from the center?
Like in the center of the sphere, sir.
What kind of sphere? Hollow, solid?
Solid, sir.
Solid sphere. A uniformly charged solid sphere. Inside the sphere, the field will be proportional to x. Okay. If I remember correctly, it is kqx by r cube. In gravitation, it is g capital M x by r cube. We use this for gravitation inside the planet. Fine. So in magnetism, if you want magnetic field proportional to the distance from a point or an axis, this kind of system can help you produce that kind of a magnetic field. Okay. And next thing, this also I think is there in the textbook, is to use Ampere's law to derive the magnetic field in a solenoid. Are you all comfortable with that idea, or do I have to explain? Ampere's law to derive magnetic field in a long solenoid. Have all of you done this? No response. Okay, let us. Mansa, you know how to derive. Someone said something. Okay. Okay, let us do it quickly. Not a big deal. It's quite simple. Consider a long solenoid. Just a moment. I'll copy the diagram. When did we discuss the case of a solenoid? This one. Okay. Just a moment. Are you all able to hear me?
Yes,
Yes,
sir.
sir.
Okay. Right. Consider a long solenoid like this. Since it's a very long solenoid, the total number of turns will be infinite. We will not talk about that. But usually in solenoids, they give you small n, which is the number of turns per unit length. Let's say that is small n for this solenoid. Okay. We need to find out the magnetic field anywhere inside the solenoid. The solenoid effectively is a collection of circular turns, circular loops. Anywhere in a circular loop, we know the magnetic field is going to be parallel to its axis. Okay, but see, consider one of the circular loops and a point inside the solenoid. This visualization is important actually. Many books, they tend to ignore this. Assume this is the solenoid. I'll just enlarge the diagram. It's infinitely long. Here in this diagram, you're able to see its ends, but actually the ends are not visible. Suppose you want the magnetic field at this point. Okay, I'm marking a point P. You can observe that it's not on the axis. And the magnetic field at that point P is the resultant of magnetic fields produced by all the loops, all the circular loops. Now consider one of the circular loops of this solenoid. Let's say this one. I'm highlighting one in blue. Consider this loop. It's a circular loop, okay? It's tightly wound. Actually, this gap will be negligible in a solenoid. It's a very tightly wound loop. So that blue one, that turn that I have highlighted is actually like this. It's a loop of current. Half of it in front of your screen and half of it behind the screen. And in that loop, how is the current flowing? Current is flowing upward in front of the screen. It's flowing like this. And the point P is not on the axis of that loop. This is the axis of that loop. Point P is somewhere here, the way we have taken it. Can any of you guess the direction of magnetic field produced by this loop at point P? On the axis, it's easy to guess. The magnetic field is going to be like this. Straight field line you will get. Away from the axis, how does a circular loop produce magnetic field? In which direction does it produce magnetic field? Any idea?
So is it leftwards?
So you are saying it will be like this. So you're indirectly saying the entire magnetic field produced by this loop is simply going to be straight lines like this.
Sir, wouldn't it be like downwards, but like left?
Okay, at point P, you are saying pointing downwards, but to the left. So you are saying it will be like this.
Yes, sir, somewhat like that.
Then will that field line not go and intersect with this? Can field lines intersect?
No, sir, no.
No, so it won't be like that. Can you think of any other shape? Yes, what do you think will be the direction of magnetic field at that point P?
Sir, can we take help of magnetic field lines?
That's what we never visualize magnetic field lines of a circular loop. That's why I'm asking what will be the shape of the field lines. Okay.
So like it will be going upwards, sir.
Okay, left but going up, you're saying. So like this.
Yes, sir.
How do you justify that? Your
So
answer
like,
is correct.
because magnetic field lines, they don't intersect each other.
Ah,
They form a closed loops.
okay, but they could all be straight lines, no?
So
Why?
like they terminate, like they originate from one point and again terminate at the same points.
So you're saying there can never be a straight magnetic field line?
Like there can be, sir.
Then
Like,
why can't they all be straight? It could produce a uniform magnetic field. Why not? Uniform magnetic field means all field lines are straight. Uniform magnetic fields are possible. Uniform electric fields are possible. Any other idea, anyone? To get the direction of magnetic field at that point P, which is not on the axis. Okay, listen. This is basically a circular loop of current, right? What do loops of current behave as? Anyone? What do current carrying loops behave as?
Collection of point charges.
No.
Not charges, like elements.
Okay, but what do they be? You can't say a system is a collection of elements. That it is obviously correct. Yes. What effect does it produce? What does it behave like?
Dipoles.
It behaves as a magnetic dipole, correct? So this side becomes south pole and this side becomes north pole for this loop. We know that. Now think of electric dipole. South pole is like negative charge. So I'll write a minus q here. And north pole is like positive charge. I hope you know the field lines between a positive and a negative charge. They originate from positive and terminate at negative like this. This is the field pattern, right? Same thing happens with magnets also, but inside the magnet it's different. Okay, like you can imagine there's a magnet here in this part. So this region is inside the magnet. Inside the behavior in case of a magnet will be different. Electric field lines, no, they don't form closed loops. Magnetic field lines form closed loops. Okay, so inside behavior will be different between electric and magnetic field. Outside behavior is the same. Fine. You can think of it this way also. Another way of looking at it. You know the electric field of a dipole, electric dipole. Let's just recollect that. Suppose there's a dipole here having dipole moment P. On the axis of the dipole, you know electric field will be parallel to the dipole moment. E is equal to 2 kp by r cube or 2 kp by x cube. E is in the same direction as P on the axis. Whereas on the equatorial line of the dipole, E is minus kp by x cube. Electric field will be opposite to the dipole moment on the equatorial line. So see, at somewhere the field is this way, at some other point the field is that way, means the field lines actually go like this. That is why the field here is like this. Here it is this way. Somewhere here it will be perpendicular to the dipole also. We had done that question. At what angle it will be electric field will be perpendicular to the dipole moment. So electric field will be changing direction. Same thing happens with magnets also. Okay. Now this is a magnetic dipole. It has south and north. The field lines on the axis, it's a straight field line, but away from the axis, the field lines will be curved. They'll be like this. You can imagine any number of field lines. Okay, that break that I have given is just to show that they are going from one side to the other side. It doesn't mean that field lines have breaks in between. They are continuous field lines. Okay. So only on the axis of the circular loop, the field line is straight. Away from the axis, they are curves. So this blue loop that we have taken at the point P, it produces a field in this direction. Okay, it's not along the x-axis. It's not completely along the y-axis also. It's at an angle like this. Let us go back to the solenoid. Now I have highlighted one blue loop there. That blue loop at the point P produces a field somewhat like this. Okay. Now we are considering an infinitely large solenoid, right? Now this same loop on the other side you take at the same distance. So you mark a point P here. There the field will be this way. Whatever angle this makes above the x-axis, the same angle that one will be making below the x-axis. They are both to the left, but one is tilted upward, the other is tilted downward. Now the same thing happens in this solenoid as well. If we have taken one blue loop on the right side, it creates a field this way. You can imagine another blue loop on the left side at the same distance. This is an infinitely large solenoid that we are talking about. So you imagine another turn here carrying a current this way. that loop at the point P creates a magnetic field like this. And since this distance and this distance are same, infinitely long, no, for every loop on this side, there will be one loop on that side at the same distance. Since these two are same, these two strengths will be same, then the net field will be this way, parallel to the axis of the solenoid. Not just at that point P, at every point inside a long solenoid, the net field created by the entire solenoid is going to be parallel to its axis. So we can visualize its magnetic field like this. Suppose this is the solenoid whose magnetic field you are asked to calculate. You can imagine its field lines this way. Okay, outside they'll curve. Just a moment, I'll draw field lines inside only, not outside. This is one field line, obviously. Other field lines will also be straight because field lines represent net magnetic field, not individual magnetic fields of the loops. So inside the solenoid, you get a field like this. Whether it is uniform or not, we'll discuss, but the field lines are going to be straight. Okay, that field strength is what you are asked to calculate or derive. Now, since the since the solenoid is infinitely large, any point inside the solenoid, it doesn't matter. Like this point P itself you take, there are going to be infinite turns on the right side. There are going to be infinite turns on the left side. It will have some magnetic field there. At the same distance from the axis, you take another point Q. For Q also, there are infinite loops on the right side. There are infinite loops on the left side. Then P and Q will have the same magnetic field. So whatever is the field at P, same will be the field at Q. So these straight magnetic field lines that are there, they have the same field everywhere along the line. Okay. So this first line has the same field all along the line. Second line has the same field all along the line. One possible change is the field may change if you come closer to the axis like this. Or if you are on the axis, you may have one field. Away from the axis, you may have different fields, maybe. Okay. But at a fixed distance from the axis, the field has to be the same. So if you take parallel lines like this, they're all parallel to the axis. So field strength will be same everywhere on that line. That is one advantage we have now to derive the magnetic field. Okay, let's consider one of these field lines just to make things clear for us. Let's take one field line away from the axis like this. Our aim is to derive an expression for magnetic field on that field line. Generally, to derive magnetic field, we have two ways. One is the element method. The other is using Ampere's law. In this case, one of you tell me which method shall we use to derive the net magnetic field at any point on that line. We need the net magnetic field there. Can we use the element method?
It will be too complicated.
What did you say? The voice was not clear.
It will be too complicated.
It will be too complicated. Why? Why is it difficult? Like Shashank, I'm asking you, what makes it complicated?
What will you choose as the element to consider?
Elements will be loops, obviously. Circular loops. The idea will be to write the expression for magnetic field of one circular loop. Let's say this one. Let's take a circular loop like this. You have to write the expression for magnetic field produced by it at that point P and integrate. What makes it difficult is that the point P is not on the axis of the circular loop, and we have no formula for magnetic field away from the axis of a circular loop yet. Okay, so we won't be able to proceed that way. The only method we are left with is Ampere's law. So we have to use Ampere's law to derive the strength of this magnetic field somewhere inside a solenoid. Okay. Can one of you quickly tell me the basic formula for Ampere's law?
Line integral of B naught B.
Integral B dot dl over a closed path. Okay. You call it closed integral B dot dl. Okay. Equal to mu naught I. So we need a closed path over which this integral becomes easy. Okay. Now from our analysis, one thing we found out is that the field strength everywhere on that straight line is same. Now our aim is to integrate this and to get the magnetic field, right? You have to get this out of the integral. If you want to get it out of the integral, you have to choose a path on which B is same at all points. Now we know on this straight line B is same everywhere. But how do we take a closed path on which B is same everywhere? That becomes difficult. Can any of you tell me some ideas? How should we take the closed path such that we'll be able to integrate and keep B out of the integral? It's slightly complicated, not that easy to get the idea, but if any of you have done it, you can tell.
You can consider the solenoid as a series of charges coming in and out, and then take the rectangle as the Ampere.
Okay, you are saying we have to take a rectangle as an Ampere's loop. Okay. See, yeah, what you said is correct only, but why are you choosing a rectangle? You can have infinite closed paths, right? Why choose the shape of a rectangle?
You can integrate, like, if the rectangle is PQRS, then P to Q, Q to R, R to S, and S to P.
Why only a rectangle? Why not a circular loop or like one straight and like semicircle, closed semicircle? Why not shapes like that? That is my question. Okay, listen all of you. Visualize the field lines inside the solenoid. They're all straight, right? Now it's possible that the field changes from distance to distance as you go away from the axis, but at a fixed distance from the axis, the field has to be the same. So what we are going to do is we'll definitely take one part of the Amperean loop like this, straight at a fixed distance from the axis. Let me draw the axis also. Okay, axis is here anyway. The gray dotted line is the axis of the solenoid. So one part of the loop has to be a straight path like this. And you visualize the magnetic fields. Magnetic fields are all along the x direction inside the solenoid. Can any of you tell me anything about magnetic field outside a solenoid?
Does it tend to zero?
Huh. But anyway, why am I talking about outside the solenoid? You can have a closed loop inside the solenoid itself like this if you want. But the problem if you take a closed loop inside the solenoid is magnetic field at this distance from the axis may not be same as magnetic field at this distance from the axis. So B won't be same all over that path and you won't be able to take it out of the integral. So you can't take a closed path inside the solenoid if your aim is to derive the magnetic field. Okay. Then how to take the path? One fact you can make use of is that the magnetic field produced by a long solenoid outside it is very small, tending to zero. So anywhere outside the solenoid, the magnetic field is approximately zero. So integral B dot dl anywhere outside the solenoid is going to be zero. Okay. So we'll make sure some part of the path goes outside the solenoid. That's fine. But the problem is you can't directly go from this straight line to outside the solenoid. You have to pass through some more points. So you have an option of going straight like this, or you have an option of taking a curved path like this to go outside the solenoid and then complete the loop and then come back inside. Okay, to complete the loop. So tell me, should we go out along a straight line perpendicular to the axis, or along a curved path also will be quite easy, will be easy to integrate? How to continue the path and go, how to continue moving and go out of the solenoid? Should we choose path 1 or path 2? And why? Shashank, you said rectangular path. So my question is, why should it be rectangular? Why should we go straight like this? Why can't we go at an angle or a curved path?
I think the integration will be easy.
Integration has to be easy. See, the magnetic field is parallel to the axis, right? This way. If you see path 1, okay, going straight out of the solenoid perpendicular to its axis, that path will become perpendicular to the magnetic field. Then B dot dl for it will become 0, because here the angle is 90 degrees. For the other path, the angle is not 90, then it simply makes integration impossible to do. Okay. So if your aim is to derive the magnetic field, you should go along a path like this. Ampere's law is valid for any path you take, but we need to use Ampere's law and the limited amount of mathematics that we know to derive magnetic field. So we are choosing this particular Amperean loop. Okay. You can apply Ampere's law over any loop you like, but to get B, you have to choose a convenient loop. So the loop will be taken like this. And once you go outside the solenoid, doesn't matter which way you go, but coming back, you have to come back straight like this. So this is the Amperean loop that you are going to take. Better take a rectangle instead of making it complicated like this. Outside, the magnetic field is anyway 0, so it doesn't matter what shape path you take outside. And now you can split it into 4 parts. Call one part as AB, next BC, CD, DA. Okay. For the path AB, which is part of this loop, magnetic field is parallel to AB. It will be parallel to DL vectors. Okay. As you move from A to B, DL will be like this. Or you can move to the left also, not an issue. We just need the magnitude of the field. Let's imagine moving to the left only. So B to A. The displacement DL will be parallel to the magnetic field, which is the orange vectors that we have drawn. Okay. Next, when you go from A to D, DL will be like this in the y direction, but magnetic field is along the orange vectors x direction. So for that part, the dot product B dot DL becomes 0. D to C B dot DL is anyway 0, because magnetic field outside is 0. C to B again B dot DL becomes 0. Either magnetic field is 0 or it is perpendicular to DL. So basically closed integral B dot DL over the entire path ABCD, or I should say ADCB. Let's take it like that. The left hand side simply becomes integral B dot DL from B to A, because for the remaining parts it became 0. Now what is integral B dot DL from B to A? That is simply integral B DL cos 0. Cos 0 is 1. And from B to A, the field is uniform. So it simply becomes B multiplied with the distance from B to A. Distance from B to A, let's call it as X. So B into X is closed integral B dot DL for this complete loop. Now we need to equate that to mu naught into I enclosed so that we can get B. But to get B, you need to know what is the current enclosed in that distance. For that, we'll make use of small n, which is number of turns per unit length. Small n is equal to number of turns divided by the length. Therefore, the number of turns in that length simply becomes nx. Each turn carries a current I. So the total current in this distance becomes I into nx. Each turn has a current I, and there are nx small n, sorry. I into small n into x. There are nx number of turns in that length, and each turn has a current I, so total current becomes I nx. Therefore, Bx is equal to mu naught I nx. X gets cancelled. you get B is equal to mu naught Ni. Okay, this is a very like common result that we use. But notice one thing, this result is independent of this distance. The distance where you take AB from the axis, it is independent of that. What it means is whether you take this field line, this field line, this field line, this one, anyone inside the solenoid, they all have the same strength. That is what it means. So you get a uniform magnetic field. Inside the long solenoid. And how much is it? Mu naught Ni. So this is how you derive magnetic field in a long solenoid using Ampere's law. This is derivation you will find in almost every textbook. But there are some things that you need to visualize. Why can't we take a loop inside the solenoid itself, completely inside the solenoid? Okay. And why is the field parallel to the axis? Even when the point is not on the axis. On the axis, the field is along the axis. We know that. Because for a circular loop, it's on the axis. It's along the axis. Away from the axis, why do we still get field parallel to the axis? Those things you need to think about. Okay, so we'll stop this session here. What all have we discussed today? We discussed some solutions to problems from the worksheet. And then using Ampere's law to derive magnetic field inside a long solenoid. Right. Your next class will be on Thursday. Thursday, we will discuss the next part of this chapter. Motion of charge in a magnetic field. What happens when a charge Q enters into a magnetic field B? What are the different types of paths it can follow? And we'll solve problems based on that. Very important stuff.